So in section 2, we're going to take what we've learned about our trigonometric graphs, and we're going to translate and reflect them. So remember, when you're talking about translation, we're talking about what happens when we have h and k in. Remember, h is a horizontal move and k is a vertical move. And when we talk about reflections, we're talking about what happens when my leading coefficient, right? What happens when a is negative? How does that change my graph? All of these things are things you've done before. You've done translations and reflections with a lot of other types of shapes. So key vocabulary here is going to be translation, reflection, amplitude, and period. All of these are things we have done before. Though I'm not sure we called reflections reflections. So you did reflections when you graphed square root and cube root functions and logarithmic functions and exponential functions, right? So you've done this before, and if you recall, it would take the graph and it would flip it over. And that's pretty much what's going to happen here. So a type of problem I might use this on is if I wanted to track my height when riding a Ferris wheel, if I wanted to track my height as a function of time, remember with the Ferris wheel, right? As time progresses, right? This is the Ferris wheel, so I'd be here, and then I'd be here, and I'd be here, and I'd be here. But when you think of it on a time continuum, I'd start wherever I got on, and then I'd go up a little bit, or maybe I'd start down here, and then I'd go up a little bit, and then I'd go up to the top, and then I'd come back down, and I'd finish back down at the ground. So in this case, this is a sine function, right, which would look like this, but you see that a sine function, and if I add this little tidbit here, this would be like the reflection of a cosine function. It would simply end there. Sine and cosine functions follow the same pattern, but they're a quarter of the period different from each other. So we'll go ahead and work on this when we get to the end of our graph after we've learned how to do these reflections and translations. So when we start talking about translations, we've got h and k again. Again, remember h is a horizontal shift and k is a vertical shift. Okay, they function the same in these as they have in all of our other different types of functions. So what we're going to do is we're going to do the amplitude. We're going to graph the y is equal to k, which is the midline, right? So before, when we worked with these, y is equal to 0 was our midline, or I think I called it a center. And then we're going to do the points. Equally, you could graph it without h and k and then shift it by h and k if you felt that that was better for you. I'm going to go straight to the final graph. Okay, so when we take it, what this looks like here, in this case, there's nothing in parentheses with x, so h is 0, k is 3. And over here, h is pi over 8, and k is 2. Okay, so when we start looking at this, I know that my amplitude here is 1, and I know that my period will be equal to 2 pi over also 1. The coefficient with x is 1, so 2 pi over 1. Okay, and in this case, they're also both a and b are also 1, so my amplitude is 1 and my period is 2 pi. That's tidy. So let's go ahead and cut our graph into quarters, right? This is 2 pi. This would be 3 pi over 2. This would be pi, and this would be pi over 2. And those are the same values down here. And 2 pi, and I have an amplitude, right? 1 and negative 1, but that's not the whole story. So in this case, y is equal to k would be y is equal to 3. 1, 2, 3. So when we start looking at our midline, that's our midline. right? And that means that my amplitude is going to be 1 above and 1 below. So 4 and 2, this is y is equal to 3. It's a sine function. It's not shifted right and left, so I can go ahead and graph. I start on my midline, then I go to my upper amplitude, back to my midline, to my lower amplitude, and back to the midline, and this is my graph. Okay, you notice that what happened? It shifted up 1, 2, 3, which was k was 3, right? So it shifted the whole thing up 3. Now this one's going to shift up 3 and right pi over 8. Oh, pi over 8, that's a pain. So if we start looking at where's pi over 8, well, this would be pi over 4, that would be pi over 8, 3 pi over 8, right? So I'm going to shift this little amount, right? All of my points are going to shift a little bit to the right. And then my amplitude, or sorry, my midline is going to go up to y is equal to 2. So my values, my lower amplitude will be at 1 and my upper amplitude will be at 3. And let me put in my midline right there. So I'm going to start here at pi over 8. I'm going to go to the next quarter plus the pi over 8, and I'll be at my upper amplitude. Then to my then to my midline, lower amplitude. And there, except here's the problem. What did I do? I graphed a sine function. No, 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 no. Cosine function starts at the upper amplitude. So I start up here and not there. I start here. A cosine function starts at the upper amplitude, so I'm starting here. And then at my next point, I'm back to the midpoint. Next point, I'm at the lower amplitude, back to the midpoint, and I finish where I started. So this comes like that. And that's my cosine function that has been shifted up to and right pi over 8. Okay, so this is what translations look like. It takes the same basic pattern and you shift it up or down, which moves the midline, and then right or left, which changes your starting point. Okay, but the other processes about splitting things into quarters and all of that, they're the same. So go ahead and practice that. Do problems 3 through 8. That's some matching work. And then graph 13 and 19. And then come on back. So when we talk about reflections, you'll notice that normally, I'm going to go ahead and show you normally, if I graphed y is equal to sine of x, right? This blue line is the graph of y is equal to the opposite of sine over x, right? It would look like this, right? And what happens is when I start in the same place, but instead of going up, when my leading coefficient is negative, I go down. That makes sense. And over here on the cosine side, instead of starting at the upper amplitude like I do, right, in a normal cosine function, I start at the upper amplitude, right, and that's what that looks like. The reflected cosine starts at the lower amplitude, right, which is logical, right? It just makes sense. Instead of 1, I get negative 1 because once I got the 1, I'd multiply it times negative 1, and that would bring me down here. Okay, now you can have reflections and translations together. You just have to do all the different parts all in the right sequence. Okay, so mostly this deals with you're still moving between the same points, upper amplitude, midline, lower amplitude. You still move one level each quarter. The difference in the sine function is you start by going down instead of starting by going up. And the difference in the cosine function is you start at the lower amplitude rather than starting at the upper amplitude. And if we were going to talk about the tangent function, this is what a normal tangent function looks like. A reflected tangent function looks like this. right? So the normal tangent function started low on the left and was high on the right. A reflected tangent function starts high on the left and goes out low on the right. Okay, so it just becomes, in this case, the reflection happens around a vertical line through the center point. And in these cases, the reflection happens around the midline. Okay, but this is the midline in a tangent function as well. Okay, so in sine and cosine, the midline is horizontal, and in tangent functions, the midline is vertical, but we're always reflecting around the midline. Okay, so let's go ahead and graph some of these guys. These are both reflected and translated, so that's going to give us practice in both. Okay, in this particular case, I know that A is equal to -1, B is equal to 1, H is equal to pi over 4, K is equal to 0. Okay, because there's nothing being added on at the end. All right, that means that my amplitude's going to be the absolute value of that. It's going to be 1 and 1. Of course, I'm not shifting up and down, but I am going to shift right and left. So let's start with the period. The period is going to be 2 pi divided by 1, so there's 2 pi. You'll notice that that happens a lot. So you should get really good at these values, 3 pi over 2. Then the whole thing is going to shift. It's going to shift by pi over 4. All right, so here's pi over 4. So it's 1/4. Everything shifts a little bit to the right. Okay, I'm still going to start here, but because my amplitude is negative, when I do my first step, I go down, and then I go up, and then here, and then here. And this is what my translated and reflected graph looks like. Okay, again, my midline was y is equal to 0 because k was equal to 0. Okay, in this particular case, I've got the same situation in terms of k being equal to 0. I have a is equal to -1, which makes it a reflection. Oh, now here's interesting. B is equal to 2, so that's going to change the period a little bit. H is equal to pi over 2. And k is equal to 0. I have to remember I'm doing a tangent function. Okay, so when I take my period, instead of 2 pi over b, it's just going to be pi over b. So my period is equal to pi over 2. Right? When I start setting up, then I want to go half of pi over 2, right, which is pi over 4. I go in either direction. Right, and this is complicated. With my h value, I'm going to move pi over 2. Right? So if I'm here, typically, I'm going to have to move all the way over to here, pi over 2. Okay? So now when I start looking at getting my, right, I move pi over 4 in either direction. This, instead of now being the right asymptote, is the left asymptote. And on the other side, I would have, so 1 pi over 4, 2 pi over 4, 3 pi over 4, 3/4 pi. And these now are the locations of my asymptotes. Okay, because what did it do? It shifted the whole period. The period was pi over 2, h was pi over 2. So in reality, this guy's equally valid, right? It's just I'm going to graph the first one, but if I go on and on in either direction, it would be here as well. Okay, then I want to go ahead and find my other points, right, halfway between these guys. So halfway between 1/4 and 1/2 is 3/8, 3 pi over 8. And this would be 5 pi over 8. All right, so I know I've got my center here. I know it's reflected, so I come in this way and I go out this way. And I have to find there's going to be a point around here and a point around there, and I don't know what they are. Okay, let's go ahead and put the midline in. I'll put the midline in as a black dotted line to help make sure that we're clear about that. And then I want to plug in to my function here. I want to plug in, I have the opposite of tangent, 2 times, all right, x in this case was 3 pi over 8. 3 pi over 8 minus pi over 2. Right? So that's 4 pi over 8. 4 pi over 8. I'm sorry, I'm making a mess up here. Right? So this is going to be the opposite of tangent 2 times, right? This is negative pi over 8. Right? 3 minus 4 is negative 1. And when I do this, this is going to be pi over 4. Well, that's very nice of them. If you remember the example I did before when I did tangent in the last lesson, where's negative pi over 4? Well, it's right here. Right? So negative pi over 4, if I find tangent of negative pi over 4, in this case, my x-coordinate is radical 2 over 2, and my y-coordinate is negative radical 2 over 2. So when I put one over the other, if I put x over y, I'll get tangent, and that's going to be negative 1. So it's the opposite of negative 1, which would just be 1. Okay, so let's go up. Let's say that's 1. That means that's negative 1. Here's a point. Here's a point. So my graph comes in along here, goes out along there. Boom. Right? And because it shifts by one whole period, right, that means that if I had graphed this without translating it, would I have had an inaccurate graph? No, I just wouldn't. It would be absolutely accurate. I just wouldn't have had the, I wouldn't have actually been working around the specific location of the center. Okay, but this does, because it's a periodic function, go on and on in every direction. If they ask you to graph one cycle, though, they want you to graph the first cycle, and that really would be here. Okay. All right, so that's reflections. I've done sine and I've done tangent. We talked about cosine a little bit. Go ahead and practice that out to 29, 31, and 40. Come back and we'll solve the problem about the Ferris wheel. Okay, so if I go ahead and I start working with my Ferris wheel information, let's talk about what's important. Right? I have my A value, I have my B value, and then I have H and I have K. Okay, so we're going to work with graphing this, right? And then we'll interpret the graph later. So A is equal to 85, B is equal to pi over 20. H is equal to 10, K is equal to 90. Whew. All right, so let's start working with a graph of some sort. So let's start here and here. We're not going to have negative time, so I'm going to ignore negative time. Right? That's not going to really happen. If I look at the amplitude, 85, right? But I've also got a shift. I have a shift that's almost the whole amplitude. Okay, so we're going to have to think of that, right? I know that y is equal to 90, right? So I'm going to put 5 here just because I know I need it. Okay, I'm going to put 90 here. And I'm going to go, right, and why did I put 5? Because this distance here is my amplitude, it's 85. Okay, and if I go 85 up, 90 and 85 is 175, right? Okay, so I've got my center line. I don't always start with the center line, but it was an easy one to start with here, and it made a lot of sense. Okay, so let's start looking at other things. So I have my amplitude. Let's look at the period. The period is going to be 2 pi over, because it's a sine function, 2 pi over b. Okay, so this is going to become 2 pi times 20 over pi. Pi's will cancel. 2 times 20 is 40. That was nice of them. So let's go to 40. Half of 40 is 20, 30, 10. It's nice that we don't have units of measure of time that have pi in them, because that would be awkward. All right, great. So now we also have a horizontal shift. So remember, I've put in my vertical shift. I also have a horizontal shift of 10. So rather than starting here on my sine function, I'm going to start there. That was nice of them. Okay, so if this is where I start at 10 seconds, and I want to go ahead and graph it, I'm going to go here and there. Uh-oh. I also have to go all the way out to 50, right? Because everything moved 10. So I'm down here at my lower amplitude and then back to 50. So this is my graph. But you'll notice I don't start at time 0. Where am I at time 0? I'm back here. Okay, so what are my maximum and minimum heights? My minimum is 5 feet. That would be, why is it at the slowest point here? Well, that's where I get on, 5 feet above the ground. I climb up a little set of stairs, there's a platform 5 feet above the ground, I can get in the Ferris wheel. I certainly don't get in 90 feet above the ground. That would be crazy, right? You could build a platform at 5 feet high or at 90 feet high. We're definitely going to do it at 5. Okay, and my maximum height is at 175. But I knew that when I went ahead and put out this point and this point, right? I already knew that. Here's my function graphed. And when you think about it, I get on 10 seconds later. If you think about the Ferris wheel itself, I get on 10 seconds later, I'm halfway up. That's 90 feet. 10 seconds later, I'm at the top. 10 seconds later, over here, I'm back in that middle point of 90 feet. And then over here, I'm at the bottom. Okay, so if I'm only going around once around, this is where I'd end up. Normally, they run you several times around. The cycle would go on until we finished. Okay, so that's working with the function of a Ferris wheel. Now, could this not have been, right? In this case, this is a sine function with both h and k, but could you see this could have been a reflected cosine function? A reflected cosine function would have done the same thing. So if I wanted to model the Ferris wheel, it would have been valid to do this sine function that we shifted to the right. But you can see that a reflected cosine function with the same value of b to create the same period and with the same value of a to create the amplitude wouldn't have had k, but it would have had, wouldn't have had h, but it would have had k. Because it doesn't need to shift from here. It's starting actually at the right place. So if you're asked to model this type of shape on your own, and create this equation, as opposed to being given the equation, you could have done this in a number of different ways. Okay, so what I want you to get used to the idea is you want to create the shape, but nobody says it had to be a sine function. This could have been a cosine function to model the Ferris wheel just as well. Okay, so it could have been a cosine function with a bigger shift. It could have been a reflected cosine function. It could have been a sine function. Right? Any of those would have worked.